Now, during the charging phase, we want to determine the differential equation and verify its solution. Let's consider the circuit of figure 6, consisting of a resistor of resistance R in series with a capacitor of capacitance C across a square generator. But during the first half period, the generator is acting as a battery, delivering a constant voltage E. The current will be delivered from the generator or from its positive pole and enters the positive plate of the capacitor marked as charge Q. So M is the positive plate of the capacitor. The positive sense is considered with the same direction. So it enters the positive plate of the capacitor. Now, let's consider the law of addition of voltage through the circuit. So UAB equals UAM plus UMB. UAB is the voltage across the generator, so it equals E. UAM is the voltage across the resistor with the positive sense, so plus Ri. UMB is the voltage across the capacitor. M is the positive plate and B is the negative plate. So UMB is the positive voltage, so plus UC. Now, when the positive sense enters the positive plate of the capacitor, we consider I equals plus the variation of charge Q as function of time. So as Q equals C times UC, thus I equals plus derivative of C UC as function of time. As C is a constant, it can be considered outside the derivative. So I equals C times derivative of UC as function of time. Now we consider the expression of I and we substitute it in the differential equation. What do we obtain? We obtain E equals R times C derivative of UC as function of time plus UC. Now we can divide by RC, the whole equation divided by RC. So we obtain E over RC equals, dividing this one by RC, we obtain DUC over DT plus UC divided by RC. So this is the differential equation that governs the variation of voltage across the capacitor during the charging phase. Now, if we want to find the differential equation in terms of another variable, let's say as function of Q, we use the same law of addition of voltage or Kirchhoff's law. But we know that I, when the positive sense enters the positive plate of the capacitor, is equal to dq over dt. And as Q equals C UC, thus UC equals Q over C. Now we substitute I by a function of Q and UC also in terms of Q. So E equals R instead of I, dq over dt, plus instead of uc, q over c. Now we divide by r. What do we obtain? E over r plus, equals dq over dt plus q over rc. This is the differential equation in Q that covers the charging phase of the capacitor. Now, if we want to find the differential equation in I, we apply the law of addition of voltage, and then we derive the whole equation with respect to time. Deriving E with respect to time, since it is a constant, so we obtain 0 equals R is a constant, derivative of I with respect to time, plus derivative of UC with respect to time. Now, as the first order differential equation consists of a variable and its derivative, like I and its derivative, here we have the derivative of I with respect to time, but we need to find I, the variable itself. So, knowing that, I equals derivative of C duc over dt, or I equals C duc over dt. So the derivative of uc with respect to time equals I over C, I over C. Thus, 0 equals R di over dt plus I over C. Now we can divide the whole equation by R. What do we obtain? 0 over R, 0 equals, here dividing by R, we obtain di over dt plus I over RC, and this is the differential equation in I that governs the charging phase of the capacitor. Now, what about the solution of the differential equation? Let's consider the first differential equation in UC, So derivative of UC as function of time plus UC divided by RC equals E over RC. Its solution is given as UC equals the maximum voltage E, 1 minus exponential minus T over tau. How to verify that it is the solution for the differential equation? First of all, we search for the derivative of UC. Let's write UC as E minus E exponential minus T over tau. I simply multiplied by E. Then its derivative duc over dt equals derivative of the constant E is 0. Now, in this function, E is a constant multiplied by exponential minus T over tau. Its derivative is minus E. Derivative of the exponential is minus 1 over tau E minus T over tau. So what do you obtain? E over tau, E minus T over tau. Now, we consider UC and its derivative and we substitute both in the differential equation. So instead of duc over dt, what do we have? E over tau, E minus t over tau. Plus, instead of uc, what do we have? This expression, E minus t over tau, divided by RC equals E over RC. So I write it here. Instead of derivative of uc as function of time, we have E over tau, E minus t over tau, plus instead of uc, what we have? E minus E minus t over tau, divided by what? By RC equals what? Equals E over RC. Now, E over tau, E minus t over tau plus E over RC minus E exponential minus t over tau divided by RC equals E over RC. Now, knowing that tau equals RC, so E over tau exponential minus t over tau is the same as E over RC exponential minus t over tau. So this one minus this one equals 0. So what do you obtain? E over RC equals E over RC. That is right. So it is verified that UC equals E1 minus E minus t over tau is a solution for the differential equation.